Hello, and welcome to Lecture 1 for CS 105, Introduction to Computer Science. So we're going to dive right in and start with Chapter 1. Chapter 0 will have its own lecture. If you want to watch it, you don't have to. I am Professor Gentry, and I am here to be here with you on your journey. So Chapter 1 is going to cover data storage and how we represent data within that storage, types of data that we're going to look at, and a lot of the information in this is related to beyond just computer technology, and it can be used in many other aspects as well. So let's go ahead and let's take a quick look at what we're going to actually discuss. We're going to look at a bit and a byte and what that means and what it looks like. We're going to talk about main memory and mass storage and kind of compare the two. We're going to look at representing any kind of value that we want to save as a bit pattern. We're going to do some exercises in the binary system, and then we're going to write a few new Python programs. So that's going to be fun. So without further ado, let's go ahead and get started. Let's talk about a bit. Now, a computer is nothing but an electronic device, so all it knows is on or off, power or no power, true and false. It really only knows two things. So we call that one unit of measure a bit, or a binary digit. It's going to have two different values, on and off. That's all you can have. So a bit pattern, on the other hand, is what you're going to use to represent the information. You're going to take those bits and add onto them or multiply them. You're going to put them in groups. So you can see here, this is a group of 8. You've got 4 and 4. That is considered a computer byte. So a byte is going to be used to represent numbers and characters and images and sound and so much other stuff. And we'll take a look at a few of those things a little later on. So when we look at computers, though, again, we can only do two things, on and off. So what we use is we use Boolean operators. And what a Boolean operator is something that manipulates to a true or false in the end. Those are the only two values that we're allowing. So that helps us kind of stay in that binary realm. There are some specific operators that we can use. There's an and, an or, an exclusive or, and a not. And a lot of these, you might have done in elementary and middle school when you say like a true and a true. What does that give you? Well, let's take a look at least the and, the or, and the exclusive or. So for the and operator, you have to have both trues in order to get a true, otherwise you get false. So if I have false and false, or a 0 and a 0, you're going to get 0. 0 and 1, which is a false and a true, they're not both true. Okay, and the same thing happens with a true and a false. The only way for an and you're going to get a true out is if all of your inputs are going to be true. On the other hand, we have an or operator. It is going to say if one or the other or both. Okay, so for a false and a false, you're going to get a false. Any other aspect, any other combination of that, you're going to get a true. So a false and a true, a false or a true is going to be a true. A true or a false is going to be a true, and a true or a true is going to give you a true. Now the difference between your or and your exclusive or is that inclusion of if both of them are true. So, your first 3 are going to be identical to the or. Your difference is going to be a true, or a true is actually going to give you a false, because you want to know if exclusively there's one or the other, not both. That's the big difference. Now, we can use these Boolean expressions to do our manipulations and to do different expressions. We can combine them by using something called a gate. And the shapes on these gates are very akin to the shapes of flowcharts. So if it is, a pointed arrow, it is definitely a not. The colors are arbitrary, but the shapes are not. So a gate is going to be the device that the computer is going to use to evaluate a Boolean operator. That's all it is. Typically, it's going to be some kind of circuit. It can be, constructed of many different materials, but this is what your building blocks are going to be made out of. Here you can see an example of the AND with its output table and the OR in the output table, the exclusive OR in the output table, and the NOT and its output table. Now the new one here that we did not see on the previous slide is the NOT, and all it does is if it is true it changes it to false, and if it's false it changes it to true. It just flips it. Now you can also expand the gate and combine them. When you start combining the gates, it's called a flip-flop. So it's going to be a circuit built from many different gates. This is what your computer memory is based on. This is how it does what it needs to do. We're going to look at 3 different examples here. One input line is used to set its stored value to 1, one input line is 0, and while both are 0, the most recently stored. So let's take a quick look at setting the output of a flip-flop to 1. So the first thing that we're going to do with the flip-flop is we're going to look at it. So we've got a NOT here, right? We've got an OR, and we've got an AND. Okay, we've got those shapes from the previous slide. So I want to make the first line a 1, so I'm turning this light switch on or making it true, and this one's going to be false. Okay, so first we're going to turn that on and see what happens. So this is going to cause the output of the OR, okay, because it's an OR, not an exclusive, this output is going to be 1 regardless, because this is a 1. Regardless of what goes on down here, it's always going to be a 1 because we used that OR, right? Remember, the only time that the OR gives a 0 is if they're both 0. Because of that, the output is going to be a 1. Now this 1 though also travels along this road and goes into the AND. You have a 0, it negates to a 1, it flip-flops on the NOT. So you've got a 1 and you have a 1 that's traveling this way. 1 and a 1 is going to give you a 1. So here you actually have a 1 and or a 1, and it's going to give you a 1. We're going to play a little bit with this with the assignment and the labs, and it's going to be a little fun, I promise. Finally, the 1 from the AND gate keeps the OR from changing the input. So here we go, we have a 0, okay, 0 of an OR. We're going to have to do this evaluation. What it did, remember, this was a 1 from before, so this changed it to 1. So again, this is not changing because even though this is a 0 up here and this is a 1, this 1 from before is going to keep it in that loop and keep it a 1 because we are with an OR, not an exclusive OR. Enough about that junk. Let's take a quick look at main memory and how we store it, what it looks like, how much we can store. So main memory is actually broken up into things called cells. This is going to be a unit of main memory. It's going to be 8 bits or a byte. So you're going to see this topic of 8 happen a lot. So we've got that happening right there. Remember 4 and 4, it's going to give us 8. The most significant bit, it's going to be the bit on the left. The least significant is going to be the bit on the right. So you're going to go from low to high. Okay, just like we do with base 10, from low to high. Where are we putting this memory? So in order to access the memory, we have to know where it is. So we're going to give it an address, just as if you were to build a bunch of houses and give them addresses. So your address is going to be a name that is going to be unique to a specific cell in your computer's main memory. So the names, they're actually going to be numbers. As you can see here, you can have something to this effect where it's like a URL. You can have something like this where it is just a byte. They're usually sequential, starting at 0 and numbering up through however much memory you have. And what that's going to do is you are going to order that memory and you're going to be able to find things much faster. Some terminology that we use when we talk about memory, we talk about RAM or random access memory. Typically, if you go into Best Buy or Target or wherever you buy your computers, you will see that this is one of the specifications, is how much RAM. And it is the memory in which that is in your internal memory, can be easily accessed in any order. It doesn't have to be sequential, but that is what is going to be there for memory in order to load your computer programs and in order to execute. Dynamic memory, or DRAM, is RAM that is basically composed of volatile memory. When I say volatile and involatile, I just mean is it erased when the computer is turned off. If it is erased, it is volatile. If it is not erased, it is involatile. So how do we measure memory capacity? So what we have here is we have basically a system built on that byte. Remember that byte is that 8 bits. We have a kilobyte, a megabyte, and a gigabyte. And now we even go up into terabytes. So a kilobyte, or a KB, is going to be 2 to the 10. Remember, we're working in groups of 2, so we want to do base 2. So 2 to the 10th power is going to be 1024 bytes. So if I say I have a 3 kilobyte system, which is 3 KB, it's going to be 3 times that 1024. The same goes for a megabyte or an MB and a gigabyte or a GB. You go from a 2 to the 20th power and 2 to the 30th power. It just keeps going up exponentially. It is much easier to say it's a 3 gig or a 3 gigabyte as opposed to 3 times the 1 billion whatever bytes. It's just a lot easier to say. So we've talked about our main memory and what's built into the computer. We also have the ability to have storage outside of the computer or in mass storage devices. We have things like magnetic disks and hard drives. We've got CDs, DVDs, magnetic tapes. There's all kinds of different ways to store information within your computer. So here there's 2 example pictures. This one is a read-write disc. The one on the right is more of a audio disc like you would play in a CD player. And it shows the differences between the two. So the audio disc that you would play in a CD player, very much like a traditional record player where the data is recorded. It's a single track. It is consecutive, spiraling through the CD. The CD is going to spin while it reads it in order. Now, on the other hand, a CD that your computer can read and write to is a little bit different. Your track is going to be divided into sectors. You've got an arm which actually can move in and out at will and find different locations on that CD as it is looking for information. Again, the disk is still spinning. The biggest difference is that this arm can find data on this CD anywhere, whereas this has to be in that continuous spiral loop. There are some great advantages. It is less volatile. It is easily portable. You can have much larger storage capacity. Some of these solid state drives now are multiple terabytes, and they're very cheap. And in I think the biggest advantage is that you can take it with you. You can put it on any computer. Typically, it doesn't matter about the operating system. It can go from a Mac OS to a Windows operating system to a Unix very seamlessly, and you can put it on a work PC, on a home PC. It doesn't matter. But how do we know what we're getting when we're looking at mass storage? So when we look at mass storage performance, we're going to look at 2 basic things. We're going to look at bandwidth and latency. Bandwidth is how much information can you get over a span of time. So I love this example of a hose. You've got 2 different bandwidth of a hose. You've got a garden hose and you've got a firefighter hose. They both do the same thing, but their output is much different. So you could think of your garden hose as being low bandwidth because you're going to have less water coming out, and the firefighter hose being very high bandwidth and a lot of water coming out at one time. The other thing that we look at is latency, and that is the time it takes to do something. So if I make a request, the latency is the time between I make that request and when the request is executed. So if I click to say open a picture, the time that it takes for me to click open the picture and the picture actually opening, that is the latency. And a lot of times with mass storage, it's how fast can the CD spin, or how fast is that arm that you're looking at that reads the information. The last kind of memory that we're going to look at when we talk about more of the mass media is flash memory. And these flash memories are traditionally very small. They're going to be circuits that are built into very, very small chambers. You can write to them and erase to them multiple times. So think cameras, think smartphones. These are kind of the main choices for those. And SD cards in particular, which is usually, I mean, an SD is a brand name, it actually stands for SanDisk, but they're going to provide gigabytes of storage on a very, very small platform, which is why they're great for cameras and smartphones. So how does a computer store this information on any of these storage devices? So there is all the information out there has to be stored in some type of bit pattern for the computer to recognize it. So you can store things like text, numeric, images, sound. You can store all this type of data as a bit pattern. It just does it in slightly different ways. Let's start out by looking at text. For text, each character is going to be represented by a unique bit pattern. And when I say character, I mean uppercase letter, lowercase letter, numeric, symbols, anything that you're going to need to type, including punctuation. There are 3 standards out there that the computers use because, you know, we get out into things when we start adding carriage returns and tabs and things like that. So ASCII is one of them, and it uses 7 bits to represent most of the symbols used for English text. ISO then expanded on the ASCII code and added another bit for an 8-bit extension to the ASCII, so it added more. And basically it started to include other major language groups, because when you're talking about some of the more character-based language groups, their letters don't quite look like ours, right? Finally, Unicode is the most universal. It is going to have the most characters. That's when you start getting symbols like happy faces and squares and geometric shapes and things like that. So now we're going up to 21 bits to represent some of these symbols used in languages. So we are going to do an example of a British pound sign that we're going to go and grab out of Unicode and put it in our program. So we'll see this one in action. Now, how do we represent numeric values? So numbers are represented using a binary notation. We've talked about this just a little bit, and we're going to represent a number in base 2. Typically, we have learned how to count and add in base 10. A computer does in base 2. Remember, because all we have is on and off. There's only 2 different things that it can do. So all numbers in a computer are stored as a sequence of these ones and zeros. So from counting from 0 to 8 using 4 bits here, I can say 0, 0, 0. This is actually a 0. This is actually 1. This would be your 2. This would be your 3. That would be your 4. That would be your 5. That would be your 6. 7, and 8. What we have down here is your byte. Remember, two sets of 4, and it is represented as 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. We'll look at that a little bit closer and get into a little bit more detail, so don't stress about that yet. Let's look at how we represent images. So there's 2 different ways that we represent images when we save them on a computer. One is through a bitmap technique, and the other one is through vectors. You may have heard these terms thrown around. Is it a bit? Is it a vector? Image? Things like that. So a bit is more of a pixel representation, which is a picture element, which is a dot. Each dot represents a single color, but the color can be changed based on luminescence and chrominescence, so how saturated that color is and how bright that is. When you stand far enough away, all of these little dots then combine to make a picture. So the more pixels or dots that you have, the more refined the picture. Now, there is a huge problem when you're talking about scaling up images. If it's a very small image and it's been pixelated, you go to zoom in and it'll create much larger squares that you see, and it's not very streamlined or accurate, really. The vector technique, on the other hand, is going to save it as geometric structures. It is much more scalable. You can increase and decrease without any kind of distortion to the image. Some of these file types are saved as TrueType and PostScript. You may have heard of those. The last one that we're going to actually look at is how we represent sound and save sound. So there are some different sampling techniques. We can save the actual sound file, or we can save instructions on how to recreate the sound. Those are two different ways that we save it. So a lot of times, based on the sampling technique, that is going to tell us how clear that the audio signal is going to be. So a long distance telephone is 8,000, whereas CD is 44,000. So a CD is going to be much clearer. And all that is it's telling us how many samples we have per second. So what it's going to do is it's actually going to save the amplitude as an encoded sound wave, and it is going to save the amplitude as it goes through time. The second way to store something is called a MIDI, and that is going to save instructions on how to recreate a sound. Typically this is used more in music, things like a synthesizer. It's going to say which instrument, which note, and how long. And so what it's going to do is it's going to actually duplicate that sound as opposed to saving the actual sound. Okay, let's dive back into the binary system. So traditionally, I think I've said this before, we have learned in base 10. So base 10 system is over here on the left with the A, and we find 1, 10, and 100. And so a 1 is 10 to the 0, a 10 is 10 to the first, and 100 is 10 squared. Okay, probably something you may or may not have learned, probably forgot. It's fine. Okay, so that's how you find your position quantities. So your representation, you've got 5 of these, 7 of these, and 100 of these. When we look at the binary system with being at base 2, we do the same thing. We go 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Oops. Okay. 1, 2, 4, 8. Okay, so we're doing the same thing, but it's slightly different. So your representation is going to be what you see, the quantity is going to be different. We're going to do a few examples and hopefully it'll help kind of sink in. Now before we go into those examples though, there is one other thing I want to talk about, and that's a hexadecimal notation. This notation is a shorthand for writing much longer bit patterns. As opposed to a base 2, it is a base 16. So we're talking 16, to the 0, 1, 2, 3, etc. In order to get 16 values though, we run out of numbers when we go to 9 because we need a single entity, right? So we dive into the alphabet, and so we go from 0 up here up to F, or down to F, I guess I should say, since it's going down. So you're going to divide your pattern into groups of 4, and then each group of 4 is going to be a separate symbol. So for here, we've got a group, here's an 8, 1, 2, 3, let's divide this into 4, okay? We can see this first one here, 1, 0, 1, 1. If I look in my table, 0, 1, 0, 0, or 0, 1, no, 1, 0, 1, 1 is going to be a B. And 0, 1, 0, 1, 0, 1, 0, 1 is going to be a 5. So what that's going to give me is it's going to give me 0x to show that it's a hexadecimal, and B5. It's just an easier way of grouping these bits together so you don't have much larger strings of these binary numbers. So let's do a few examples of converting to binary. Let's start out by going through my method of how I convert binary numbers. Slightly different than what's in the book, but of course I like mine better. So you count with binary just like you do with base 10, except you go between zeros and ones. So let's do a quick count. 1 is going to be equal to 1, and then we're out of numbers, so we have to roll the numeric in front of it. So it would be 1, 0, and that's going to be 2. 1, 1 is 3, and then again we have to go 1, 0, 0 is 4. We keep doing that. So here's 5, 6, 7, and 8. So you can see each time you increase the number of numbers, that's where your exponent is starting to come into play. So here you've got 2 to the first, 2 to the second, and 2 to the third. Expanding those exponents gives you 2, and then 2 times 2, which is 4, and 2 times 2 times 2, which is 8. So you can see how they correlate together. You can see the exponent actually corresponds to the number of zeros. So here you've got 1 0, and it's 2 to the first, 2, and it's 2 squared, and 3 zeros, and it's 2 to the third. Let's do our first conversion. So we have the binary number 100, 101. Let's convert that into tens. First, let's select out the ones that have an actual 1 in them, because those are the place values that we're going to be concerned with. From here, we can find the position and the position quantity. So for the first position, it is 2 to the 0, which is just 1. For this position here, it is 2 squared. And for this position over here, it's going to be 2 to the 5th, because it's in the 5th position. Next, let's calculate the value of each one of these positions that we have a 1 in. So 2 to the 5th is 2 times 2 times 2 times 2 times 2. And that's going to be equal to 32. 2 squared is 2 times 2, and that's going to be 4. And then we have this lingering 1 out here. All we have to do now is add up those three values, so 32 plus 4 plus 1, and the tens equivalent is going to be 37. Now let's go the other way. Let's start with a decimal and convert it into binary. I've put some charts in the notes, so you might want to take a look at those. Let's start with the number 13. I like to convert this way by setting up a few of my binary values just so I can get started. Let's pull out the first 5 binary values. So 2 to the 0 is 1, 2 to the first is 2, to the third is 8, and finally 2 to the fourth is 16. Well, we can immediately see that 16 is greater than 13, so we don't need that location anymore. Let's exit out. What we now do is we start dividing the value of the base 2 into the decimal. So 13 divided by 8, 8 goes into 13 one time. So we move that 1 up into the binary position. You then subtract the 8 and get whatever remainder you have left over. So left over here we have 5. Next, we moved on to the next value in the base 2, which is a 4, and we take our remainder and divide it. So 5 divided by 4, 4 goes in one time, the 1 becomes the binary number. We subtract 4 from 5 and we get a remainder of 1. Again, we do the same thing. This time we take a 2 and we say 1 divided by 2. Can 2 go into the number 1? No, it can't. So we put a 0 in the binary number. Finally, we do the same thing with the 1. So 1 divided by 1 is 1, and we put the 1 in the binary number. 1 minus 1 is 0. We're done. So in the end, the decimal number 13 is the binary number of 1101. Easy, right? Now let's jump into programming, and we're going to do a little bit of programming here in just a second. So let's take a look at data and programming. So a programming language is a computer system created to allow humans to tell computers how to do those instructions. Okay, so basically that is going to be the way that we're going to tell the computer how to execute those instructions that we are requiring and to go ahead and do what we need it to do. So we're going to take a look at something called a programming language called Python. Python is going to be a popular programming language for applications, scientific computations, data science. It is a very good introductory language to use with students. It is a free language available out there at python.org, and I have another video as to how to choose the interpreter that you would like to do. That brings me to the point that Python is an interpreted language rather than a compiled language. We go way more in depth into this in Introduction to Computer Programming. What it means is that it is a line-by-line execution as opposed to a full program that is compiled all at once and then executed. So for example, our first command that we're going to learn is going to be a print. You can see here the print is a built-in function with Python. Print is just going to mirror back anything that you put within the parentheses, and here we're going to put a string. If you want a string to just be spit back out, you're going to put that string within quotation marks. Whatever's in the quotation marks, it's just going to spit right out. So that is how Python is going to show you that it is a string, by using those quotation marks. So that's going to be a value. So let's take a quick look and put this into a Python code. Now, I'm going to start out with Python Anywhere. There is a much better explanation in a whole video that I have out there that is linked, but we can go ahead and get started with some consoles. So let's select Python and 3.8. This should take us to a Python console. So it's going to load the interpreter, and when you see the 3 arrows, you know you're ready to go. I can go in here and type print with my quotes, hello world, and then I can hit the enter key. Once I hit the enter key, you can see that line has been executed. It mirrors back the words that I put into those parentheses, or those quotation marks, and in the parentheses, and it just says hello world. Let's go back to our PowerPoint real quick, and let's take a look at different variables. So a variable is a value that we're going to use throughout the program, but we may not know exactly what that value is. So we're going to give it a name, and anytime we reference that name, we mean to use that specific value. So a lot of times it's identical to the mathematical variable. So where you say x equals 4 and then you use x in a mathematical expression, it's exactly what a variable is. So let's look at a few of the different ways that we have variables. The first line here is called an assignment statement. Okay, the use of the equal sign can be a little misleading if you're confused about programming, but really it is an assignment statement in programming. An equation is a different symbol. Little confusing, but in general, an assignment is going to be a single equal sign. So what we're saying here is I am assigning the value of the string hello world to the variable s. The next thing I'm going to do here is I'm going to print that value. So what do you think is going to happen? I don't know. Let's try it. So I'm coming back to my Python window here, and I'm going to say s equals quote hello world and then I'm going to say print s. It just printed the string that I assigned it. Okay, super easy peasy. So let's take a second and talk about variables. So Python has some very, very simple rules when it comes to creating variables. So they must begin with an alphabet letter, so either uppercase or lowercase. It can have as many characters as you would like, and once you start with that character, you can then put in numbers and symbols. Doesn't matter. Now, the only symbol you're allowed is the underscore, so that's fine though too. So while you can do something like what is here where it just says s equals, typical programming etiquette says that you're going to create a variable with a more descriptive name. So, you know, you can have something called my integer, my float, my boolean, my string. You will see when we get into doing some conversion programming that we're going to give it very specific names so that you can tell what that variable is and what it's holding. Now, Python is case sensitive. So if you're going to start it with a lowercase, then you need to keep that lowercase throughout the every time you use that variable. So uppercase in my integer and all lowercase my integer, two completely different variables. The other item that you have to keep in mind is keywords. So Python has some very specific keywords that are used in order to give it instructions to do something else, such as the word print. So you would not want to use those keywords in variables. You can find a whole list of keywords out on the python.org website, and it's a very few, kind of makes sense of why you wouldn't want to use those. The last thing I want to point out about Python with this slide is that Python ignores all white space. So if I were to type my integer no space equals sign 5, that is the same as if I would type my integer space equals space 5. It just ignores any kind of spaces and white space, and all it really looks for is that return. Typically we do put in those spaces in order to make it easier for the human eye to read, as opposed to really the computer needing those spaces being there. Now, we've got some different things that we can do. There's a few different new topics on this slide, so let's take them one by one. So number one, we've got something here with the pound sign. That is going to be a comment. Anything after the pound sign, the interpreter is going to completely ignore. The pound sign is there for the programmers and those that come after you that want to update your code. So anytime you want to put some type of comment, you use the hashtag or the pound sign. The second thing that we have is that you can actually do operations within that print statement that we looked at. All we really did was input and output text with the quotation marks, but you can do something like print 3 plus 4. Now there are no quotes, so what it's going to do is it's actually going to add those and print the number 7. The same thing here with subtraction. Multiplication is the star, division is the slash. Now there are some, when it comes to division, there are some division and other mathematics, there are some unique cases. So a double star is going to raise to the power. So this is going to be 2 to the 10th. Okay, like that. Sorry, I can't write with a mouse. Okay, so it's going to be 2 to the power of 10. This right here is going to be our division. So this type of division is going to give you the decimal place, okay? A double slash is going to give you the whole number only. So 45 divided by 4, technically, if you look at it in decimal form, it is 11.25. But if I give it a double slash, it's going to give me the 11, the whole number portion of the answer only. Now, in order to get the remainder is going to be a percent sign. Now, it's going to give you the number remain. So notice it is going to be different than, it's not going to give you the decimal value. It's going to say, okay, 4 goes into 45 11 times, which is 44. There's 1 left over. It's going to give you the 1 left over, okay? In mathematics, you would take that remainder, put it over what you're dividing, and that's going to give you 1/4. That's going to give you your 0.25. Quick, easy math lesson. Okay, so another thing you can do is you can actually manipulate strings. So let's say s equals hello plus world. Let's do an s equals s times 4, which is going to take this and do it 4 times, and let's see what happens. X equals hello plus world. X equals X times 4. Print X. Okay, so it's going to take that hello world and do it 4 times. Let's do a quick Python program and go through a currency conversion. Now, I'm going to do it a little bit different in Python Anywhere. So let me go into that layout. I am going to create a new file as opposed to doing the console. So I can open another file, I can give it a name. Now, when I do this, if I do it this way, what I need to do is I need to give it a file extension of a .py. That indicates that it's going to be a Python file, and This way I can actually save my work as opposed to when I work in the console. The console is nice to just go ahead and play, but it is nice to save your work sometimes. So if this file does not exist, it is going to go ahead and create a new one. So let's create a new file with Python. Now, there's a few different things to see here. You're going to have, it's not going to run your interpreted program as it did in the console. It's going to be slightly different. Up here in the top, you're going to have some save as, and you're going to have a run button. You're also down at the bottom going to have a run this file. So let's go ahead and type in for the currency converter. So we're going to go ahead and start out with that comment. A converter for currency exchange. Okay. Now you can see here it doesn't do anything until I actually tell it to run, so it's a little bit more like a compiled program than interpreted. But let's go ahead, US dollars to Great Britain pounds equals, let's do, and then we can do a tab, and let's put a comment at the end so we know what it is. Okay, you can see in the Python Anywhere, it is changing all of the comments to a single color so that you can tell visually what is being ignored and what's being used. So let's keep going. Pound sign equals. Now, we want to use a special character here because we want to use the British pound sign. So it is going to be a Unicode sign. When we use Unicode, we are going to do the quotes just like we would do a string, but we're going to do this special character in front of it of a /u. The /u is going to tell the Python interpreter that this is going to be a Unicode number, and we're going to give it 00A3. Okay, and we're going to say that it is going to be the Unicode value for pound. The last thing we're going to do is we're going to do dollars, and we're going to give it 1,000. And I'm going to give it, a number of dollars to convert. Okay, so I've assigned all my variables. You can see, remember, they are case sensitive, so when we use them coming up, you need to make sure your cases match. I'm going to go ahead and start out with another comment, and I'm going to say conversion calculations, and I'm going to put the actual expression. So pounds is going to be equal to dollars times USD to GBP. Okay. So what that's going to do is it is going to take the exchange rate and multiply it by the dollars. Last but not least, let's go ahead and print the results. So we're going to use our print keyword, which we've used before. Now we want to build a string. We want to say, we want to have some words, we want to use some values that are in those variables. So let's start and say in string and put today, comma, and we need to put the $sign, okay, because the $sign is not included in that numeric value. Okay. Now we can just add to it dollars. Okay. Now, one thing that you'll notice in the PowerPoint is that we need to explicitly tell it that we want that dollars to go from a numeric to a string. That's what this str is going to do. And then finally, print converts to, and we're going to put a space, right, plus the pound sign plus, we're going to make it a string again, and then pounds. So let's go ahead, let's save this, and let's hit run. Okay. Today, $1,000 converts to $660 in pounds. Easy peasy, you just made a whole new Python program. Congratulations. last but not least, we are going to have errors, unfortunately. It's just going to happen. There are 3 different types of errors that we typically look at when we're talking about programming. Errors are finding errors and correcting them. We call this debugging. Typically, there are syntax errors, semantic errors, and runtime errors. So syntax error is going to be a typo, or something that was typed in incorrectly. You're going to get something that says syntax error, invalid syntax. So as you can see from the first one, 5 plus what, right? The second one that we have here is that we spelled print wrong, so it's going to give you an error. Now, a semantic error is a little bit harder to find because your interpreted code will execute, and you may have something like an incorrect equation. So your total pay equals 40 plus extra hours times pay rate. Okay, what you're going to need to do is put some parentheses around here, 40 plus however many extra times your pay rate, or maybe you'd get time and a half, so that would mean that this equation is incorrect. Runtime errors are usually seen at runtime when the code is executed, and that'll be things like if something ends up being 0 and you try to divide by it, or an unintentional divide by 0. That's all I have for lecture today. I'm going to put another quick video up on how to look at the assignment and lab 1, so take a minute and review those as well.